Well, again, everyone, and welcome to today's presentation on safety compliance in machinery rooms and refrigeration applications. For those of you who may not be familiar with Bacharach, we are a global leader in the design and manufacture of precision gas detection instruments. We make refrigerant monitors for a variety of applications, including refrigerant leak rate reduction, think supermarkets or other high-volume refrigerant users, refrigerant leak detection in occupied spaces, specifically occupied spaces that are using a VRF system to condition the space, and of course, refrigerant safety compliance in machinery rooms, which we will be discussing today. During today's webinar, we will be covering the following content. First, we will discuss why safety compliance is so important in refrigeration applications. Next, the presenter, Tom Burniston, will compare the requirements of the two international safety codes, ASHRAE Standard 15 and EN 378. Afterwards, we will discuss what buyers look for when deploying a gas detection solution and how applications may vary. Finally, Tom will introduce Bacharach's newest product line, the MGS-400 gas detection series, and we will conclude the presentation with a brief question and answer session. So let's get started. Today's presenter is Tom Burniston. Tom has worked in the gas detection industry since 2004 and has experience in a wide variety of applications, including refrigeration, HVAC, and the oil and gas industry. Tom has been with Bacharach since 2014 as the product manager for our portfolio of refrigerant leak detection products. Additionally, Tom writes on gas detection for industry publications and has an article on refrigerant safety compliance in the current edition of Detectors. If for any reason you don't speak English, that article is actually on our blog. So welcome, Tom. It's great to have you with us here today.
Thank you, Matt. Thank you very much for the introduction. It's great to see that we've got lots of people on to talk to today about refrigeration gas detection.
Absolutely.
What we'll focus on today are the particular aspects of the standards that focus on refrigerant leak detection. It's probably worth mentioning at this stage, of course, that the standards are much more wide-ranging regarding the whole refrigeration system than not just focusing in on the leak detection part of that, but there are specific clauses within there which we'll highlight and discuss that do relate directly to detecting refrigerant leaks. So hopefully we'll be able to provide some useful information to everybody in terms of where to find that information and how to effectively use it and drive forward their compliance position. So we'll push ahead and actually look at what the requirements are within the refrigerant safety codes. Now the standards vary and are specific to each region. Some specific ones to highlight are EN 378 in Europe, ASHRAE 15 within the US, B52-13 standards in Canada, and the Japanese Refrigeration Association 4068T standards in Japan. Now, of course, there are a wider range of standards than these across the globe, but this is just to highlight that there are those standards out there regionally. But what we do tend to see is that the requirements surrounding refrigerant detection tend to be broadly similar across the different regions. And what we'll focus in on today are in particular ASHRAE 15 and EN 378. Now, if we look at why we are detecting for leaks of refrigerant, it boils down to the simple fact that there can be danger present if a leak is undetected and there is no action taken in the event of a leak occurring. Now, those dangers do vary depending on the particular type of refrigerant being used. Very commonly used, of course, we see HFCs or hydrofluorocarbons, which have been in the market for quite some time now. Now, we're not going to focus in here on any of the aspects regarding global warming potential and the environmental impact. We are going to look at safety here. And when we look at HFCs, the primary risk to personnel for most of these gases is asphyxiation or oxygen depletion at high concentrations. And then a lot of standards, particularly those, again, we see driven within the US, We also see an occupational exposure limit typically in the range of 1,000 parts per million for most refrigerants. That tends to be broadly the same for the HFOs, or the hydrofluoroolefins, which are coming onto the market more frequently now. But there's an additional element of risk within these that people are focusing on within the industry regarding the fact that many of these gases are mildly flammable. It tends to be typically in fairly high concentrations and with a relatively low flame propagation and high ignition temperature, which means we find the A2L classification, which defines these as mildly flammable refrigerants. CO2, of course, is a very old refrigerant and has been coming back into the market more prominently now. We do see regional differences in terms of how widespread the use of CO2 currently is. In particular, in Europe, we are seeing a very high percentage of new systems going in using CO2 as a refrigerant, especially in the food retail industry. Obviously, it has a much lower global warming potential than many of the HFCs. But of course, CO2 can present some risks as well. There is a risk of asphyxiation. CO2 presents an immediate danger to life and health at 40,000 parts per million, and the typical exposure limit for CO2 is generally around 5,000 parts per million, which is where we would typically tend to see systems going into alarm from. Ammonia, of course, is broadly used in industrial refrigeration applications, and ammonia presents a unique set of dangers compared to the other refrigerants typically used because it is toxic at fairly low concentrations, with an exposure limit typically in the region of about 25 to 35 parts per million. We do see variances in different geographies within that kind of range, but it is typically that low level that we're looking at a risk being identified. There is an immediate danger to health at 300 parts per million, which we can see is much lower than for the other refrigerants out there. And of course, with ammonia, there's also a flammability risk, with ammonia having a lower explosive limit of 15.4% by volume. So a large leak, of course, goes beyond that toxic risk and becomes a flammable explosion hazard as well. So broadly speaking, these are the reasons we are looking for refrigerant leaks. It is because of the range of hazards that can present themselves if there is a leak from the refrigeration system. So let's look at ASHRAE Standard 15 and look at the refrigerant detection requirements within there. I've highlighted here some of the key definitions from within the standard. These are just to give relevance to particularly where we tend to see leak detection being employed. So a machinery room, of course, we should all be familiar with, is the space that is designed to house the compressors and pressure vessels that drive a centralized refrigeration system. An occupied space, of course, is fairly self-explanatory. It is that portion of premises that is accessible or occupied by people, but the one thing to note there specifically is that the occupied space definition excludes machinery rooms, and there are some specific references within the standard that are focused in machinery rooms. And the refrigerant concentration limit is important. This is the definition of the concentration in air that is determined to present a risk. So the limits in place are calculated there to reduce those risks of acute toxicity, asphyxiation, and flammability, which of course we've just mentioned with respect to the different gases that are being used. A couple of references regarding occupancies. A large mercantile occupancy would typically be what we would define a supermarket or a large grocery store within. An industrial occupancy is a premise which has controlled access and that's used to manufacture, process, or store goods. So this is typically where we would see refrigerants in applications such as food processing and industrial cold storage, and this falls into cold rooms and walk-in freezers within smaller applications as well. Then a mixed occupancy is where we have two or more of these different types within the same space. Key thing there being the most stringent requirements for those occupancies are the ones that come into play for all of them. So if we look at the clauses within ASHRAE 15 that are primarily reflecting what we need to do on a refrigerant detection level, Section 7.2 defines that the refrigerant concentration limits should not exceed the amounts within ASHRAE Standard 34, which of course can be referenced. What we particularly are pulling out here is that in Section 7.2.2, we see that the refrigerant concentration limit does not need to apply in an industrial occupancy or refrigerated room if certain conditions are met. And as we can see, one of those conditions, which is clause D within here, is having refrigerant detectors installed within the space, essentially meeting the same requirements as are defined very specifically for detection within a machinery room. So what we can determine here from ASHRAE 15 is that within an industrial occupancy, when it comes to refrigerant detection, we're essentially employing exactly the same parts of the regulations and standards that apply to machinery rooms. So if we look at that part of the standard, this is section 8.11.2.1, determines here that a refrigerating machinery room shall contain a detector. The language there is important. It is defining a mandate here by use of the word shall. And this detector should actuate an alarm and actuate mechanical ventilation if a leak is detected. And that leak should be at a value no greater than the corresponding time-weighted average levels, which typically tend to conform to the occupational exposure limits we touched on earlier. Key things here to note are that in the event of an alarm, visual and audible alarms shall be activated inside the machinery room and outside of each entrance. So it's important to note that the entrances to the space also need to provide a warning to personnel, not just within the space. And there was a note in there as well that the alarms should be reset manually from within the machinery room. So the summary points here would be that a machinery room requires detection in all instances, and cold rooms require detection when a refrigerant leak could exceed the practical limit or the refrigerant concentration limit within that space. And the detectors must actuate the audio-visual alarms inside and outside each entrance to the room, and must actuate mechanical ventilation in the room. And we can note from the last part of this clause that the alarms must latch and they must be able to be reset from inside the monitored space. So if we then compare that to the primary European regulation here regarding refrigerant safety standards and leak detection, EN 378-3, the 2016 version, we can see here that the requirements are predominantly the same as we see in ASHRAE 15. Occupancies are defined differently, but ultimately give us broadly the same results, and you can find those in section 5 of this standard. And the gas detection clauses within there are in section 9, and they link into sections 8.1 and 8.3, which define the alarm system behavior. But to cut to the chase, the only practical differences between these two regulations are that within the European standard, cold rooms only require alarms inside the monitored space. There is no specific mandate within there to alarm audio and audibly and visually outside of entrance. And if in the event of a detector failure, the alarm sequence must be triggered also. So if we were to summarize the EN 378 refrigerant detection requirements, detection again is required when a refrigerant leak can exceed the practical limit. Machinery rooms again require audio and visual alarms both inside and outside of the room. It's not quite as explicit as ASHRAE 15, but we would see typical safety practice to include an indication outside the entrance to the door, but that outside location could technically be in a supervised location also. And the code also determines that detectors must actuate mechanical ventilation. As we just mentioned, cold rooms in the EN 378 standard require audio-visual alarms inside the room. The classification there is as an occupied space and would be category C within those occupancy classifications. Although it's not mandated, we would typically expect to see an indication outside of the cold room door in the event of a leak as well, even though it's not mandated by the regulations. And of course, as we mentioned, the detector failure should trigger the alarm sequence. So we'll touch on here what you should look for in a gas detection solution to help enable the compliance with the codes. Now, there are lots of gas detection products available on the market, but there are some key factors to consider when looking at the specifications and selecting something to use. We of course need to ensure that the detection levels available on the device are under the limits specified in the codes, and we would advise that you look to make sure they're significantly under those limits as well, because then you allow for tolerance within there, and you can ensure that you're on the right side of safety by alarming before you ultimately have to from a code perspective. But typically, we're talking alarming under 1,000 parts per million for HFCs according to ASHRAE 34. And in EN 378, the practical limit will typically tend to be in the percentage range for HFC there as well, although we would typically expect to see people alarming at much lower levels than that. It can be very useful to look for ensuring audio-visual alarms being directly on each detector inside of the machinery room or the cold room. This really comes down to a case of convenience and simplicity of installation of a system. It really cuts down on the hardware and installation requirements from having to install additional devices for each audio-visual alarm that is required. But of course, you do need to be able to drive those AV alarms outside the entrances to the machinery room or the cold room. Typically, what you'll need to do there is look for a gas detection controller that is working with the devices that can either provide those alarms or drive them. Or you could be looking to use additional horns and strobes, which most typically would be actuated by relays on each gas detector that will trigger in the event of an alarm and provide that additional audio-visual indication outside of the monitored space. Of course, we also need to be ensuring that we're actuating mechanical ventilation in the machinery room. This again can be done using relays directly from the gas detector or from a gas detection controller. But this, of course, can be driven by a building management system or front-end control system. And in order to do that, you want to be looking for connectivity from your gas detection system, either via relays, via an analog output, via a Modbus connection, some way of actually presenting that alarm status into the building management system in order to actuate those additional measures. And of course, we do want to be looking for alarms to be configurable such that they can be set to latch for a manual reset from inside the machinery room or cold room. And what we mean there by latching is that when an alarm state is in place, it requires that manual reset. It doesn't automatically come out of alarm if that alarm condition is removed. And it also means that we shouldn't be looking for something that you can unlatch and disable an alarm from outside of the monitored space, because the code is quite clear that that should be done from within the space where the detector is. So I'll have a quick look here at some application and configuration examples. Now, I would say here that we have to bear in mind that what we're showing here is far from exhaustive, because there are a myriad of different layouts and room types and room sizes that we will find using refrigerants. But some of the typical things here to try and bring to life what we're talking about in the regulations, we'll try and step through. So if we look at a small machinery room with a single entrance, we can see here that essentially we need a gas detector to be inside that space, some power onto the gas detector, and from there we can be looking at driving a power and relay signal to an additional horn strobe to give us that audio-visual alarm outside of the entrance as is required within the code. So this is a fairly straightforward and simple one for us to look at. If we then look towards a large chiller room, if we're talking a large chiller here, it may be that we're ideally looking to have more than one gas detector in there to maximize the chance of finding a leak and cover more of those points within a system that may be more prone to leaks, which is typically the joints and valves and flanges within a system. But if we look at this room here with two entrances, we can see that with the gas detectors within the space, we have those audible and visual alarms. And we can power and communicate to those just with a single controller outside of one of the entrances, which again is able to provide that audio visual alarm requirement. But from there, of course, we can drive power and a relay signal to an additional horn strobe outside another entrance. So we can very easily here have a system that is centralized and controlled from one place, rather than having to have multiple systems giving you difficulty in terms of driving the collection of audible and visual alarms. If we look at a cold room example, say we're looking at two cold rooms here side by side. Again, we need a detector in there with the audible and visual alarms, and we can communicate to and power those from a single controller. And given the proximity to the entrances here, a controller can be used here to provide the AV alarms for both of these, most particularly if you're looking at a controller that has the a specific indication of in which room you have a refrigerant leak occurring, which again ensures that you have that information, that visibility of where there is a potential danger. If we throw on another entrance to each of these cold rooms, we can see that the setup stays broadly the same, but again, we need to be looking at adding on the additional horn strobes into the system here, so that we're providing those audible and visual alarms outside of each entrance into the refrigerated space, which of course again falls in line with those ASHRAE 15 code requirements. Add on the machinery room to a cold room setup, and of course we again need to have the gas detection within the machinery room as well as those cold rooms. But we can see here it's possible to again centralize that whole system with indication within one controller by running both power and communication lines back to that, simplifying the installation such that there is only one primary power connection that needs to go in, but enabling the gas detection that you need and enabling all of the power and relay signaling that you need outside of each entrance within the machinery rooms and cold rooms. We get into an even more complex system here, and we can look at a large machinery room with two entrances into there. And again, with that kind of space, we probably look at two detectors being needed there for best practice. But the most important thing in there in terms of the code compliance, of course, ensuring that we have the audible and visual alarms with the horn strobes outside of each of those entrances. The same then being seen in the cold rooms, running off the centralized refrigerating system. And as you can see, we have the gas detection in each of those. We have the horn strobes outside of them. But when you start to get to this kind of system, it may be that you need to look at including some additional power connections, just in terms of the load that's needed from one particular line and the spacing of that across a large site. And then, of course, large cold storage facilities we must remember as well. So if we've got a machinery room here driving a large facility, we typically expect here to see a detector mounted in the airflow, the return airflow of each evaporator within the room. And again, they can be daisy-chained with power and communications back to a centralized controller, and that can then run out to a machinery room as well. And we've got the AV alarms that we need outside the primary space through the gas detection controller, and we can use that additional horn strobe outside of the machinery room there. So, as I mentioned, we have not an exhaustive list here. Sorry, go ahead, Matt.
Tom, excuse me. So we have had a question come in from the audience about applications. One of the attendees would like to know about the detector placement for a machinery room that is using ammonia.
Okay. Well, ammonia is lighter than air. So in the event of an ammonia leak, we would typically expect to see the gas rise to the ceiling in the space and do so fairly quickly. One of the key things to look at within any application, whether we're talking about ammonia or other gases, is to look at what the airflow is. So although we would expect to see gas accumulate close to the ceiling, in terms of where those detection points are in relation to where the leak is most likely to come from, we would want to look at that placement with regards to what the airflow within the room is as well. Oftentimes it could be that we will see a higher level ammonia detector placed up closer to the ceiling where the gas is going to accumulate, but it wouldn't be uncommon to see the lower level sensors in the 30 ppm alarm region for toxic levels monitored actually lower down, because although the gas is going to rise in terms of that human risk and human exposure, that is going to be where people are breathing. But of course, if you have multiple levels within a room with access platforms and such things, those need to be considered as well. So we do need to look at the physical properties of the gas. We do need to look at the airflow within the room and also where a leak is most likely to arise from. But it's really a case of taking those rules and applying them to a specific application. Because of the different layouts we can have here, there's typically not one hard and fast rule that you could state that in any ammonia application, this is where you put your placement of detectors. It really can be better to look at it on the layout of the room, where people are going to be, and as I say, it may be that you want to place the toxic level detectors and potentially the higher range flammability level detectors in different places pending that specific application or layout. So we'll have a look at the MGS-400 gas detection series, which is the new solution from Bacharach, which is really designed around enabling and enhancing and easing the capacity to comply with the refrigerant safety codes out there, such as ASHRAE 15 and EN378, but to do so in a very intuitive way, which takes some of the mystery out of gas detection and essentially enables people to feel that they have a very easy, very straightforward system to set up, use, and configure. So if we look across the Bacharach portfolio for leak detectors for safety compliance applications, so the MGS-400 is brand new and supersedes some of the older products in the Bacharach platform, such as the MGD-100 and MGS-150. But still within there we have other options. The MGS-250 uses an infrared sensor, which can add some benefits regarding absolute stability and accuracy, and also removing cross-interference from other background gases and atmospheric effects that can influence some sensors. The MGS-550 is really differentiated through having the ability of having two sensors there on one detector. That can be particularly useful, actually, coming back to the question on ammonia applications, to enable a single gas detector to have two sensors on there, one in that lower toxic range and one in the higher flammability type ranges, which can be placed in different locations by using remote sensor cables on there. There are also solutions out there for using in occupied spaces, such as hotel rooms, which typically will arise when VRF systems are used, which are growing in popularity around the globe. But our focus here will be what I guess we would define as the more standard machinery room and cold room type applications, chiller room applications, where the MGS-400 would be the most straightforward and applicable solution. When we talk about the range here, there are three different detectors within there: the MGS-410, the MGS-450, and the MGS-460. Broadly across these, the primary features and modes of operation are the same. Just a few key differentiating factors, which really come down primarily to communications. The MGS-410 communicates only via Modbus, more designed for integration into controller systems or BMS systems. The MGS-550 adds in relays and an analog output, which allows it to be used more as a standalone solution. The MGS-460 mirrors the MGS-450, but is slightly different in that the sensor is mounted in a different enclosure which can be mounted remotely from the main electronics, which again could come into use when there's a difficult to access area for where the gas needs to be detected, but in terms of for configuration and installation purposes of the electronics, it's easier for maintenance purposes and installation purposes to mount those in a different location to where we actually want to detect the gas. The MGS-400 really, as I mentioned, is very specifically designed to help equipment owners meet the needs of the refrigerant safety codes such as ASHRAE 15 and EN 378. They can be integrated with the MGS-408 controller or a building management system. And they do provide all the audio-visual alarm requirements as detailed in the standards, and all of the control and mitigation requirements in the standards are covered here through effective use of the system. So all the outputs are there for triggering things such as the mechanical ventilation, the additional audio-visual alarms that are needed in order to comply. A lot of the design here really has been focused upon how time and therefore money can be saved when using these systems. Installation is very simple. There are multiple cable entries within the enclosures, which allow for a very straightforward way to daisy chain the power and communications within the systems. And it's worth highlighting here that the MGS-400 platform has separate terminals for power going in and out of the system, and for the digital Modbus communications going in and out of the system. So it's very clean, very easy, and very straightforward to connect the wiring and install the system. Commissioning is incredibly fast and intuitive. No special tools are needed. The days of using multimeters or voltmeters and adjusting potentiometers to configure a gas detector are gone with the MGS-400 platform. There's also no manufacturer unique tools that are needed here that need to be bought in addition to the detectors. The primary thing being here that we tend to find nobody really wants to read the manual for these things, and with the MGS-400 they won't need to. The commissioning process here is incredibly intuitive using a mobile app, which we will go into in a little more detail in a couple of slides' time. Maintenance is also very, very simple. Pre-calibrated sensors are used here, and they can be exchanged in a plug-and-play manner within the detector. And we can compare that to being as easy as changing a light bulb. And there's a lot of time saved here in that what would typically on this type of gas detector have used to take about 30 minutes to perform a full zero calibration and span calibration on a system using certified calibration gas, which of course I must state is still possible with this system and runs on a semi-automated system with no manual adjustment, but a lot of time can be saved by using the pre-calibrated sensor exchange here, and that can be done comfortably in well under 5 minutes per detector. So there is a vast labour and time saving to be had here, which of course translates through into cost savings as well. No specialty training is needed for using the MGS-400. It is very simple to use. I mentioned the intuitive app communicating via Bluetooth, and that's used for configuration, calibration processes, real-time data view on the system. There is an output test mode to provide functional tests of all of the detector's communication and output capabilities, and there are diagnostics in there which proactively help troubleshoot any issues that may arise. And the plug-and-play sensor modules that I mentioned have got a poker yoke design, which essentially means there is only one way to put those into the system. It is physically impossible to install them in correctly, which again means there is no special training needed to perform that very quick, that very simple sensor exchange. There is only one way to do it, so it cannot be done wrong. The performance of the MGS-400 series is absolutely focused in on being optimized for refrigeration applications. Response times in here are optimized by mounting the sensor in a sealed manner at the front of the system, right where the gas is going to permeate through to it. That means there's no dead space into which the gas must diffuse before a sensor gives a response. So if you were to look at a system that is a sensor open within a housing, that gas has got to start to fill up that whole enclosure there before we're going to get an accurate response. This is as close really as we can get to having a raw sensor open in the atmosphere. But of course we've got the protection here of the IP ratings of the system to ensure that we maintain the responses, but the responses will be quick. Also important that the sensors are designed in a suitable way for the applications they're going into. And we have low temperature performance on the MGS-400 such that these can be installed and work effectively in environments down to -40 degrees Fahrenheit or -40 degrees C as well. Also important to note that the MGS-400 on all sensor types includes temperature compensation, and that can mitigate false responses due to changes in temperature, whether that be an ambient change or a process such as a defrost cycle. Many gas detectors that are out there using similar types of sensor technologies can generate a false response if there is a temperature shift, and this is mitigated and managed within the MGS-400 series by monitoring the sensor temperature and adjusting the outputs in accordance with how the sensor reacts under those temperature changes. It's also important to be keeping up with the refrigerant market. We are seeing through various policies and programs out there, such as F-gas in Europe, the SNAP program in the US, the larger push on natural refrigerants, but it's important to be able to be agile in characterizing new sensors to monitor and detect for the new gases that are being used within the market. And of course, we can say with the MGS-400 series that even if you were to update your system to be using a new drop-in gas from one of the newer refrigerants to the market, very easy to just update the detection system by using those pre-calibrated sensor modules to swap in and out of the system for any new gas coming to market. And on the screen here, we can see a list of the current gases that are supported by the MGS-400 platform and the technologies that those sensor types are on. As you can see, that's pretty wide-ranging, but of course we're maintaining the agile capacity to characterize new sensors as new refrigerants come onto the market. So we would always encourage anybody who has a need to speak to us, because of course those laboratory capabilities are important to be able to do that and ensure that we have the solutions in place. And one of the key things here with the MGS-400 that takes a leap forward is the mobile application that allows that intuitive communication with the systems. It connects to all the MGS-400 gas detectors, and it is available on both Android and iOS platforms. I'd note that it's a free app as well that can be downloaded from the app stores, and it gives that intuitive interface. We can see here on the main screen that you'll see in the app, we're going to get the gas type, we're going to get the current gas measurement and the status on there of whether we're okay or whether we have any alarm thresholds being surpassed there, which will be indicated with color coding as well as text on there. And there are also ways in here to acknowledge alarms if they're in place and to go in and view the full device information as well, so pulling out things such as the serial numbers. And there is a user configurable alias within the system here as well, so you can name each detector to tie it into the specific location or asset that it is there to monitor. Lots of information is available to extract from the app, including information on any faults that have occurred, the instrument details of type and serial number, and the sensor types, of course, are detailed separately as well because they are that interchangeable module. Also got firmware versions within there, and you can view current alarm set points that are configured. And one thing that's pretty important here as well is we have a calibration due timer. So there will be a countdown here that will provide an alert to you to advise of when maintenance should be undertaken on the system. Any gas detector should be regularly maintained. It's also mandated under a lot of regulations that should take place. And the MGS-400 via the mobile app can proactively help you in managing the timing of that. We can also initiate calibration and bump test with the system here, both 0 and span calibrations, and they will be performed automatically once they have been triggered. The app here also allows the generation of a field calibration certificate, which can include the gas details, the company name, both of the person doing the calibration and of the end customer. Logos can be loaded into there. We can use the app here to provide a full audit trail for any maintenance done with the system. And one of the key things here then again is the output test mode here. We've got a manual functional test here to ensure that things such as the audible and visual alarms are functioning as they should, relays are activating and connected properly to things such as the horn strobes, the mechanical ventilation that we've spoken about. And you can adjust the analog output level and mode here as well to provide, again, the functional test if that's in use. But one of the probably the key thing here is the ease of device management and configurability. The alarm set points here are defined via a simple entry of a number, no calculations on voltages, no adjustments of potentiometers, no restrictions of using dip switches. Everything in here is just a simple, intuitive entry. We also have the alarm behavior configurable as to whether it should be latching, as we discussed is needed for machinery rooms, or non-latching. Modbus settings can be adjusted in here to ensure interaction with any control devices. Relay behavior in terms of normally open, normally closed, fail-safe. This can all be configured here within the system. So if we summarize in terms of what you should look for in a leak detection solution, key questions to ask: does it meet the requirements for the refrigerant safety standards with regards to detection and with regards to alarming? So here we want to be looking for audio-visual alarms on board the gas detector. We want to look for the ability to connect to and interface with additional audio-visual alarms via a controller or via a horn strobe. So we have the that capacity both inside and outside of the machinery room or the cold room. We want to ensure we can configure the alarm to be latching. We want to ensure that we have a system that operates effectively in low temperatures, such that the same system can be used in a machinery room and in a walk-in freezer or a cold storage application. So we just have one system type within a facility. And of course, we need to make sure that the system is capable of detecting under the required limits and with an appropriate response time. Next thing we want to look at is it simple to install? Is it simple to commission? Is it simple to configure? And is it simple to maintain? So we want to be looking for no special tools that need to be used. We want to be looking to make sure that we have the appropriate cable entries and terminal connections such that it's effective and simple to install a system. Interfaces such as a mobile app for configuration and test will really provide intuitive simplicity in multiple languages that really remove the mystery and complications surrounding gas detection. And when we look at maintenance, those pre-calibrated sensor modules are a real time saver and again remove that need for any specialized training. So that's the end of our slide deck today, but we'll move on to a Q&A session and encourage anybody to push forward any questions to us that they have now, and we'll answer as many as we can within the time remaining.
All right. Well, thank you, Tom. That was a great presentation. So we have had a few attendee questions come in. So the first question asks, why are diffusion detectors more appropriate than aspirated systems for safety compliance?
Okay, thanks, Matt. Well, the first thing I'd say is there's There's not really a reason that we would say diffusion detectors are more appropriate than aspirated systems for safety compliance. An aspirated system can be very effectively used in a safety compliance application. What we would typically tend to see, however, is that an aspirated system will most often monitor at much lower levels than a diffusion type sensor because of the technology that's used. Now that allows benefits in terms of aiming more at reducing leak rates as well as achieving safety compliance, but it does tend to come with a higher cost, particularly if we're looking at a smaller application where maybe we have one machinery room to monitor, one chiller room to monitor, and if the focus is on safety compliance, the diffusion detectors will provide sometimes a more cost-effective way of achieving that compliance. But an aspirated system, if employed effectively, can also be used in the safety compliance application. Key things to look for there would be minimizing the sample time between different zones or channels on that aspirated system. So looking for something that has a quick sample transport time and a quick sensor response time can enable that to ensure that those safety needs are met.
Okay, thank you. So another attendee asked, what is the relationship between the RCL and the OEL for refrigerant? And I believe they're asking about one of your early slides about the dangers of refrigerants.
Okay, thank you for the question. Well, the OEL is, as we probably most of us know on here, the occupational exposure limit, and that tends to be defined as what is safe for somebody to be exposed to over the course of a standard 8-hour working day. The refrigerant concentration limit tends to be based upon, and it depends a little bit which regulations we're looking at. If we take that from the ASHRAE 15 view, most of the time here the refrigerant concentration limit will actually be the same as the OEL. If we look at it from the European standard perspective, the refrigerant concentration limit will typically tend to refer to the limit at which acute toxicity or asphyxiation or flammability is an issue. So this does vary depending on the region that we're talking about. In terms of the need for gas detection, we will find that the calculation will be done based on the charge size of the whole refrigeration system that could potentially leak into the one single space, an industrial occupancy or a machinery room. And if that maximum concentration in the event of a catastrophic leak can exceed the refrigerant concentration limit, often, as I mentioned, tied into the OEL, then that is where the need for detection becomes mandated and very apparent within the systems.
Okay, great. Our next attendee question asks, why is it important that leak detectors are designed to operate at cold temperatures? So obviously, you mentioned that the MGS-400 series is designed to operate down to -40 degrees. Why is that important?
It really comes down to being able to use a system across multiple applications. We will typically tend to see that most frozen applications will have temperatures in the region of about -18 or about -28 degrees C. I'm afraid, being a European, my brain is working in those terms rather than in Fahrenheit terms. But we will see a number of detectors on the market that use sensors which are only certified for use above freezing point, or sometimes at temperatures that don't even get as low as freezing point. So what this means is if you have a facility that has a machinery room, which would typically be at more of an ambient temperature, but then also has cold rooms, also has freezer space within there, you can end up with a variety of different systems in place that make it harder to maintain, harder to track, and harder to integrate a system than if you're able to use one system in all of these locations, which has the capacity to monitor in the environmental conditions that are found all across this application. And it also means that for anybody who's monitoring multiple sites or maintaining systems across multiple sites of different types, there can just be one type of system that is familiar and straightforward to use and maintain across all of those different application types.
Okay, great. All right, we're going to take time for one last question. Obviously, if we've not been able to answer your question, please go ahead and ask that, and someone from the Bacharach team will follow up with you via email. But our last question is, with the MGS-400 leak detectors, can they be utilized with leak detection rates or log in order to meet logging requirements?
I'm going to infer a little bit from this question that we might be talking here about looking at the leak rates from a particular system or asset, potentially in line with the reporting requirements under regulations such as the EPA's Clean Air Act, Section 608. There is some difference here in terms of actually calculating a leak rate, because a leak rate would most typically be calculated based upon how much refrigerant is recharged into a system rather than what is detected by a leak detector. Ultimately, a leak detector is going to see a concentration of gas in the air at the location that the leak detector is placed. So it's not going to, for example, be able to quantify how much gas has leaked into a space over a period of time. That really would come from tracking the refrigerant usage. But what you can do here with a leak detection system to feed into that is link the leak detection system into the refrigerant tracking requirements such that you can show when a leak was detected and track from there when it was repaired, show that it is not present anymore by the fact that the leak detection system is not showing any further leaks, and then also track from there how much refrigerant was entered into the system. I would also note on here that the MGS-400 series does provide some data logging on the system as well via the MGS-408 controller, which enables a tracking over time of any particular leak events that have been seen.
Okay, well, I think that's where we're going to have to end today's presentation. For more information about safety compliance in machinery rooms and refrigeration applications, and to learn about how Bacharach can help you achieve compliance, visit www.mybacharach.com. Tom, thank you again for joining us to discuss refrigerant safety compliance, and thank you again to all of our attendees for joining us today. Take care and have a great rest of your day.
Thank you, Matt. Thank you to everyone for attending.